Good morning, everyone. I hope you're enjoying a full day of physics today at the QuarkNet Masterclass. Today I'm going to go through a quick overview of how to analyze data using the iSpy tool. But before we get into that, I want to just stress the importance of keeping this cheat sheet on hand. This is an online one, but you might have a hard copy. You've been bombarded with a lot of information about how to analyze these events, but it's really simple. All you got to do is just keep referencing back to this, and eventually you'll get the hang of it. Now, the analysis itself is only going to involve four particles. You've got the electrons right here, muons right here, neutrinos, and then for the Higgs only, you've got the photon. And all you got to do to actually figure out what event these are recognize these different particles. The W events have the added complexity of also determining the charges of either the electrons or the muons that are within them, but that'll be very easy, and we'll cross that bridge when we come to it. So right now, let's jump into the tool. And the first thing you see is this 3D model of the detector. You can actually pan around it and rotate it by clicking and dragging. And you can zoom in either with your scroll wheel or with these magnifying glass tools right here. And then you can also kind of change your perspective. So this is kind of a perspective view where when you zoom in, you actually phase through the detector, kind of like Kitty Pryde from the X-Men. Or you can go into this version where when you zoom in, all that really happens is the detector gets bigger. Both are kind of useful in different situations. It doesn't really matter which one you use. With that, let's start analyzing some data. So hit the Open File button in the top left corner. Hit Open Files from the web. And I'm going to be using the Masterclass samples, but you should choose whichever one you're assigned because mine are only 8 samples and they're very, very specific. So then click your event. It might take a while for these to load, by the way. So click your first event and hit Load. And you see this mess, and you really don't know how to analyze it. And I wouldn't know how to analyze this either, and that's why we're going to clean it up first. So go into this sidebar here, scroll down to Tracks, under Tracking, turn that off. Turn off everything in the HCal. The HCal does not matter for what we're doing today. Then turn on Photons, Missing Energy, and make sure Electron Tracks is turned on. Now, another thing I like to do just to kind of have some sort of reference point within the detector is to turn on eCal barrel, just so it's especially good for this missing energy vector to kind of have something to compare different ones to. So I would turn that on. And you can also turn on or off the event, which all it does is give you a timestamp for when this data was recorded. I just find that very interesting because it reminds me that this is real data. Like, I don't know where I was September 30th, 2010 at 12:35 Greenwich Mean Time, but science was going on, apparently. Very important science indeed. So with that, let's get into analysis. So let's go into this straight down the barrel view of the detector and zoom in a little bit. And what we see is this long purple vector here, which is our missing energy vector, which we often interpret as a neutrino, but in some cases we won't actually. And then we also see this electron track right here, this green electron track with a deposit in the eCal. That's actually a vector for how much energy was deposited by that particle when it slammed into it. So we've got those two things. And if you look on your cheat sheet, if you see a neutrino and an electron, it means a W decay. But the W decays, you also have to figure out if it's positive or negative. So in order to do that, you have to find the charge of the lepton that's in it. The neutrino is neutral. Neutrino, neutral. But for the electron or the muon that makes up the W decay, you have to find out if it's positive or negative. And to do that, you find out the curvature, because this entire detector has a magnetic field in it that's curving the tracks of these leptons. And if it's curving clockwise in this view, this straight down the barrel view, which is this first perspective button, if it's curving clockwise, it's a positive particle. And if it's curving negative, if it's curving anti-clockwise, it's negative. If you zoom right in here and maybe put a piece of paper to the screen or something like that, just a straight edge, you see that it's actually curving clockwise. So this is a positron, and that means that this is a W plus event. Pretty cool. And let's go into the next one. And we also see this missing energy vector, indicating a neutrino, very large, larger than the last one. Keep in mind some of these sizes, by the way. And then you see this electron again, and large deposit in the eCal. Then you zoom in, we can tell that that's a W decay because of that. And if we analyze the curvature of this one, we can kind of see that it's going anti-clockwise. It's going around. So that's a true electron. So that means that this is a W minus event because you've got the neutrino and you've got the the negatively charged electron. So it's a W minus event. Now if we go into the next one, we see this familiar missing energy vector here, but then you might be asking, what is this giant red thing right here? Well, that giant red thing is a muon, the heavier cousin of the electron. It goes further through the detector. It's got a lot more inertia. So this is a muon, and if you look on your cheat sheet, a muon and a neutrino would be another type of W decay. So just like the other ones, we're just going to analyze the curvature. It's a little easier to do with the muon, actually. And we can see that it's going clockwise, so that is a W plus event. Then the next one, it's pretty much exactly the same as the last one. You've got this missing energy vector right here, and you've got the muon. This is definitely a W decay. You can analyze the curvature on your own. Let's just move on to the next one, because the next one is very interesting. If you look on your cheat sheet, there's no event that has 2 electrons and 1 neutrino. So you got to make a decision here. You got to find out which one of these is negligible in order for this to be an actual event that you can analyze. So let's take a good look at these. First, let's start with this missing energy vector. If you'll notice, it's a little smaller than some of the other ones we've seen. And just due to the nature of it, remember, this isn't directly detecting a neutrino. All it's saying is that due to conservation of momentum, something has to be here with this amount of energy. It doesn't necessarily mean it has to be a neutrino, and the smaller it is, the less reliable it would be to call it a neutrino. And then if we look at these electrons here, you'll notice that they both have 2 pretty high energy deposits in the eCal, and actually if we click on them right here, you can analyze their momentum. And the momentum of this one is around 24, and the momentum of this one is around 26. Those are pretty close together, right? And those are pretty high momentums actually in this scenario. So that would kind of indicate that these aren't to be ignored. And then if we zoom in here, we can actually see that they're curving in opposite directions. And if you look at your cheat sheet on the Z decay, the 2 leptons that make up the Z decay have to have opposite charges because the Z is a neutral particle. So that would mean that 2 particles that are curving in opposite directions would kind of indicate that that's a Z. So I would definitely, in this scenario, say that the neutrino or the missing energy detector isn't a neutrino and that this is a Z decay as opposed to a W decay. In the next one, we see 2 muons, which is another type of Z event. Z can happen with either electrons or muons. And you see they're both curving opposite directions, which would make sense. Then the next one, it's basically the same thing. 2 muons curving opposite directions. You'd call that a Z particle. So this final one is very fascinating because it kind of has one of everything in it. It looks a little similar to the last heavy analysis one that we had, where you have these 2 electron tracks, then you've got this missing energy vector. But if you pay a little bit more attention to it, this missing energy vector is a lot bigger than the last one that we encountered. And then if you also look closely, you see these 4 little yellow lines. You see 2 of them next to the missing energy vector and 1 going off with each of the electrons. And you might be wondering what those are. Those are photons, and photons, for our purposes, are only really involved in the Higgs decay, and they have 4 photons. So you might be tempted to think, maybe this is a Higgs decay. Maybe this electron, and this potential neutrino are all negligible. But then you can also go and take a look at the numbers. So if you click these electrons, this one has an energy value of 5.7. This one has a value of 7.4, 34.1, and 91. Those are all very different, very inconsistent, and they should be around the same. But if you look at these 2 electrons, this one's 33.9, the momentum, not the energy. And this one, that's the photon again. Be very careful. Is around 30.7. So those are very close. So if you look at this, maybe you can find a way to say that this is a Z. They are curving in opposite directions. So that would definitely work. But again, it's something that's completely up to you. You need to look at the data and analyze it for yourself and use your logical reasoning. You know, some of these aren't going to have a straightforward answer, and that is what is so fun about a lot of these. So I'll let you get to analyzing some of your own data. You've got about 100 of these to go and very little time to do it. Have fun, and may the force be with you.